Okay.
Okay, let's start. Yeah. Okay, so it's a great pleasure to me to introduce FabioTal from University of São Paulo, preserving homeomorphisms of the closed channels. And I think this is not the last, but there is another talk next Friday, and I think that it's the last one of this period. So, okay, please, Fabio.
I think that there are two more talks.
Two more talks?
We have
okay.
Godofredo next week, and Karina Marin, the last session of July, and okay. Then we will restart with Henri Zarig in September. So.
Okay, so thank you, Alejandro, and thank you, Lorenzo. Thank you, everybody, for the invitation. It's a pleasure to speak here, and I think these seminars have been a very good thing that happened during this pandemic, and I understand everybody had a lot of trouble adjusting. I have some trouble adjusting, so please stop me if it's not comprehensible, or if you want to ask questions. This usually helps me get my rhythm when speaking about stuff. And I'm going to speak today about the work that I did with Jonathan Conejeros, which is in Santiago. And it's called Albury-Mato sets for air preserving homeos of the closed annulus. I'll explain a little bit more what I mean by all of these in starting. But let me just start with some pictures of, well, the idea is to study area preserving maps of surfaces sometimes, or just area preserving maps in dimension 2. And then you want to see what is the typical kind of things that you observe. And if you start, well, there's one very standard family called the Chillicothe-Taylor standard map, which is it's given here by this formula. You just say it's just a shear in the vertical in the first coordinate, and the second coordinate you add some perturbation by alpha sine of 2 pi x. Oh, just a reminder: every torus for me is the two torus, or the circle is usually just R mod Z, or the circle is R mod Z, meaning that it has length 1, and the torus is R2 mod Z2, so that it also has length 1 in horizontal and vertical coordinates. And if you start iterating this map and looking what the phase space looks like, then you have these kind of pictures. You see stuff like some periodic disks, some islands, and some other regions in between these islands, which are filled with something like, looks like a sea of more chaotic things. So you have some organized things and some sea of unorganized things, and sometimes you have that this sea of non-organized things take up the whole space in some sense. So exactly what are we seeing here is, let me try to describe a little bit of the qualitative behavior, is that first you see these periodic topological disks, which I was calling islands in these pictures, and they are usually associated with elliptic periodic points. You have some elliptic periodic points, you have sufficient differentiability, you should have some KAM invariant circles around this. And this is the second thing that we could see, is that you have some invariant curves around these islands. So these islands have several invariant curves, and these curves usually represent things which are rotating with different speeds. So if you go back here, you see here that you have one big island, and you see these circle line things are orbits, which you see, and these are kind of this is not foliated by lines. In between these two lines, you have some chaotic region, but these different lines have different rotating speeds, saying that when you look at this island from some iterate where it's fixed, then what's happening is that the points are turning around some fixed point there, and the rotation time, the time it takes for points there to rotate is varying, and it's not constant. You have some different rotating speeds. Okay, and as I said before, in between these curves, you usually have some kind of diffusive behavior, some region which is not does not look like a line, does not look like something we found interior, but some places where you expect to have, well, perhaps dense orbit, the orbits which are dense in an open set with this diffuse region, or at least look like you have some orbits which are dense in an open set. It doesn't really need to be like that, but these are the sort of invariant topological annuli that you see when you do these things. In between the two curves, you have some invariant topological annuli. And as I said before, sometimes you have this more complicated region when you, which, for instance, in this case, okay, in the last case, when you have the diffuse region is not an invariant topological annuli, but it's sort of all the topological structure of your surface. So what's my question here is that, okay, so can we describe what kind of dynamics is present in this complicated regions, these diffusive regions? And the approach here will be to try to use rotation theory. That is, try to understand some invariant objects and relate them to the rotation speed that they have in these regions. Especially when you have an annulus, we will see there is a good way of describing what is rotation speed, and we'll try to understand what kind of invariant objects, invariant specific dynamics you can find looking for these objects as related to rotation speed. It's an interesting approach because it's mostly a topological theory. Well, at least the way I'm going to do it now, it's going to be mostly topological. It's strange, it doesn't need much differentiability. It's nice because I'm very bad at differentiating stuff, so I can use just topology, which works better for me. So in any way, so just a reminder, I believe everybody knows this, but just to remind people what's rotation theory. So that's the most old case is the case of Poincare rotation number. And then when you have the homeomorphism of the circle that preserves orientation, and you have a lift of this homeomorphism of the circle to R, then you can compute what's called the Poincare rotation number, which is just by looking at R, and then you see how much the point is moved. So you take a point X and see where A of X goes, and then where A2 of X goes, and you look at how much you moved, and you divide by the time that you moved, it gives you a speed of how much you're moving to the right. And
Fabio, it's possible your connection has some problem. A bunch of people complained it's a little noisy somehow.
My connection is noisy?
Oh, it's better now somehow. Yeah. Can you check the chat?
Now it's much better when you answer, Fabio.
Okay.
It's
kind of
much
stops
better,
sometimes.
You can switch off the videos.
Not
If I
clear.
switch off my video,
Not clear.
No, the other
Because
way.
everybody quite well except
Somehow now it's clear than when you just explain math. Now it's clear. It's better.
okay. Okay, I'm not sure what I should do. I'll start again.
Now it's very good, Fabio.
Yeah, no, it's very good.
Sorry.
It's very good.
Yes.
Okay.
Sorry.
So, okay, I'll come back. So I was saying we have this Poincare rotation number. I guess everybody knows what Poincare rotation number is. It just explains what speed you're turning around the circle. And as you mostly know, I'm sorry, they started renovations today in the apartment block. So if you're hearing this construction sounds, I have nothing to do with that. I try to ask them and they cannot change. So
Fabio,
you have.
sorry, I think that I guess that you moved to some place, to the wrong place, but now the sound is again back.
Okay.
Sorry for bothering you.
Wait, let me try to do something like this. Wait a second.
Maybe there is some equilibrium point in, I don't know.
Probably it's your microphone.
Probably.
No, it's always bad. When he speaks, it's bad. When everybody else speaks, it's okay.
So the problem comes from his connection, obviously.
Or maybe.
So
It's-
maybe everyone should turn off the video.
No,
Look, Jacqueline, it
No.
won't help. It won't help because I hear you very well. I hear Lorenzo very well. So it's in Fabio. It's in him. Maybe if he uses earphones.
Yeah, okay.
Do you have earphones, Fabio?
If I have earphones, yes. 1 second. I'll get
Sometimes
some.
it helps.
Just 1 second.
Fabio? Okay.
Okay. 1 second. Is this any better?
For now, yes.
So far,
Yes,
much
okay.
better.
It's okay. It's okay now.
But thank you.
Okay. So let's go with this, Control L. So as I was saying, the Poincare rotation number, luckily this is something everybody knows, so I can go fast and not skip too much time here. So we have a Poincare rotation number. If every point has a rotation number in the situation, and this rotation number is the same, it does not depend on the point, and you have some dynamical properties associated with that. If the rotation number is rational, that means that you have a periodic point with that, you have periodic points, and that's if and only if. If it's irrational, then you have at least a minimal set, and dynamics is conjugated to a irrational rotation. Okay, and this is very classical. So we try to work now, and what I'm going to try to work is homeomorphisms of the closed annulus, and I showed you before homeomorphisms in general of surfaces, but if you have islands, then you usually have these invariant curves, and in between two curves, you have a closed annulus. The idea is trying to study that. So just to fix notation, A is going to be the closed annulus, and tilde A is it's a universal covering space, which is just the strip. So I have the annulus here, and then the strip is tilde A. And then we have a map that goes from here to here, which is phi, which is the projection. And I'm just using P1 as the projection on the first coordinate. It's just how in the strip, not in the annulus, you just say, okay, so how far along the strip am I? And then I'm usually going to work with an OMO of the annulus, which is isotopic identity. That means here just that the top boundary is sent to the top boundary, the lower boundary is sent to the lower boundary, and it preserves the relation. Okay? And a fixed lit is the sound input, or kind of. Okay. Not sure what I can do. I try to close everything else. I'll speak slowly. That just might help everything else. Okay. Okay. I have a fixed lip, which is I lift this OMO from the annulus to the strip, and then I can define something which is called the displacement function, which is how much a point has moved. If I have here A, and I take a point Z here, and I look at where it ends, f of z is here, then I just measure how much is the displacement on the horizontal. This is a function which is actually defined on the annulus. I took a point on the lift, but it's the same. Doesn't matter which lift of a point in the annulus you take, this displacement function is the same. So you're just saying, okay, given this large f, how much am I moving to the right when I apply my OMO once? Okay, and then this is the basic objects which we'll need to define rotation in different ways, but I want to keep in mind two simple examples. The first example is this one. Whenever I speak, it's nice to think of two things. This is just I take a OMO, which is a time one map of this flow. It's annulus. It moves the top boundary. Everybody moves one. It's 6 points, but they move one to the right. The lower boundary, everybody is a fixed point in the annulus, but below, everybody's moving one to the left. And everybody goes from the top boundary. Everybody which is in the interior, it starts at the top boundary and ends at the lower boundary. Okay, it's a simple map. It's a very simple way to see it. And the second example is just integral twist in some sense. You just have invariant lines, and the rotation speed is different. Each line is invariant. Each line is a circle in the annulus. Everybody is rotating with different speeds. Top boundary is moving one to the right. Lower boundary is moving one to the left, and everybody in between is moving with a proportional speed, depending on how far you are from the top boundary to the bottom. And let's use this as reminders of calculating some velocities here. So let me start with this rotation theory. Let me start with some idea. First, I will look at rotation from the point of view of measure. So I have a set of invariant measures for my own mill. This is my mu of f, which is there, the set of invariant probability measures. And then I have mu r of f, which is the set of ergodic invariant probability measures. It's that again. Not sure. Let me try something. Okay, 1 second. Sorry again, and just sort of kick out the kid from class, but it's okay. Let's see, this improves. Is the sound better now? No? Is the sound any good now? Yes.
Now it's much better, Fabio. I think that now is good. At least
Now we
Okay,
hear
so
you.
maybe the camera when it's pointing at me gets the sound better than when it's pointing at the.
maybe.
Okay.
Okay, thank
Okay.
you, Fabio.
Okay, I'll lose my board and just use the camera. Okay. Thank you. Sorry, guys. It used to work before. It has to happen on the presentation. Okay, so I have this set of invariant measures, and I can define what is called the rotation number of a measure. It's just average how much every point is moving in one direction. Okay, if you take the average of the displacement function, this gives you what is called the rotation number for a measure for a whole middle of the circle. And well, this is always defined when just because this is always defined. It's integrating function. Function is defined, and you can define first something called the measure rotation set, which is all the rotation vectors you see as rotation vectors of measures. And since the set of invariant measures is convex and this application is linear, this is going to be an interval. Because it's a convex set of R, this means that is usually a closed, it's a compact convex set. You apply a linear transformation, this is going to give you a compact interval. And that's called rotation, the measure rotation set. And then is bad again. You see some faces. And then you have the ergodic rotation is still bad. Maybe I can try disconnecting and connecting again and seeing if it helps, but I'm not sure. Should I try to do that? if no one can hear me, was it good? Was it good before when we were talking at the beginning of the seminar?
Somehow now we hear you, then you start speaking a lot, and after a while it starts breaking.
And I think that you also are approaching to the computer when you are speaking. I don't know what is.
Perhaps it's the microphone volume. It goes up in the roof and it becomes distorted.
Maybe.
I don't know.
If I speak not that loud, it works better.
I think that now is very good.
Now it sounds good.
Now
yeah.
it's very good.
I don't know. You
Okay.
can do this doing.
Maybe I get excited and speak very loud. I'll try not to be excited and speak lower. Okay.
Sorry.
So then you have
Now it's
the
very good.
ergodic. Now it's very good. Okay. I'll keep looking at faces and see if people complain. And if people complain, then I know it's time for me to get less excited. So, and then you also have the ergodic rotation set, which is just the rotation set of all measures, all rotation numbers for measures which are ergodic. And these are two different kind of ways of measuring rotation.
Sorry, Fabio. I think that it's a matter of movement. The microphone is touching your cloth, maybe, because when you speak,
I'm not using this microphone.
Okay, but when you,
I'm not using this microphone.
you are not using. So
the microphone is in the camera.
Because when you speak, it's in the camera. Okay, because when you start to move, it starts some problems. But I don't know. It was a suggestion. I don't know.
But I think that the microphone is in the camera. Is not connected to me. I won't move and just keep very still.
I know that it's against your name, Fabio, but
sorry.
No, I say
when you was writing down in the paper, the audio was fine.
So I'm not. I can forget the. Is the audio fine now?
Now it's good.
Yes.
Now it's perfect.
So we have the measure rotation set, the ergodic rotation set. These are rotations measure when you use measures. But you can also define rotation number for points. These are more typical things. When, for instance, when you have that's the typical way you do it for Poincaré rotation numbers. So now in the annulus, you say that a point have a rotation number if you take the average displacement it has on the horizontal and you calculate it, and it has a limit. And in this limit, if this limit exists, you say that this is the rotation number of a point Z. Okay. What's different from the case of the annulus? Bad again? Is it working? Okay. What's different from the case from the circle is that now points do not need to have a rotation number. It's not clear that points need to have a rotation number. It's not that easy to understand, to see an example, but I'll give an example soon. I have no idea what I can do here. If it's that bad, I can try to connect again and see if it improves, because I just see ugly faces on my screen all the time. So I'll connect again and try again. Okay, one moment. Yeah, and okay, so I'll calm down and settle down, and I hope that the sound is good. And, I'll do the joke about the software engineer and the car problem afterwards, but and you can define rotation number from a point just taking the average of how much you move to the right for a point. The thing is, rotation numbers do not need to exist. Points do not have to have a rotation number. They might have different average velocities, and sometimes accumulating one side, sometimes accumulating the other side. And more than that, rotation numbers do not need to be equal. It's very easy to find situations. The two examples, top boundary, you have a rotation number of 1. Bottom boundary, you have a rotation number of -1. They are moving at different speeds. This is not like the circle in the two examples I saw before. And you have something called the punctual rotation set, which is, okay, let's see all that rotation numbers for different points. You look at every point and see, oh, what kind of rotation numbers can you see here? So, but this is a rotation from the point of view of points as average velocities and not average displacements. And you call this rotation set of a punctual rotation set. And there's a final one, final rotation kind of set, rotation set kind of I want to speak about, which is rotation of compact sets. So you say that a compact set has a rotation number if every single point in that compact set has this rotation speed. That means you have some, usually you have an F invariant set, and you say, okay, if this compact invariant set is such that every point in this compact set has a rotation number and it's the same, I'll say that the rotation set has a rotation number rho. And we also say that rho is realized by a compact set. I could say for every rotation number, I say, oh, rho is realized by a measure, or rho is realized by a ergodic measure, rho is realized by a point, and rho is realized by a periodic set, by a compact set. And typical examples of compact sets that have a rotation number are periodic orbits, but even minimal sets do not need to have a single rotation number. It's not clear that you're going to have a single rotation number for a minimal set. You have examples where you have minimal sets that do not have a rotation number. And then I'll define this as the Aubry-Matter rotation set because of the similarities of the Aubry-Matter theory of twist maps. If it's the set of rotation numbers that are realized by a compact set. So is the sound good now, or is it bad, or is it okay? Okay, it's good. Great. And then you can have a simple proposition, which is this hierarchy of different rotation sets or different ways of realizing stuff. You can the rotation set by measures is easier. It's the smallest, it's the largest one, and then it contains. Oh, this is all wrong. It should be every contained here should be. It's the other way around. It's a subset. It contains instead of contained. Sorry. And if you have a point that has a rotation measure, a rotation number, just take the typical limit Krylov-Gogulyov process. You find a measure which has the same rotation number. So that the rotation number of points are always rotation number of measures. You have an ergodic measure that has a rotation number. A typical point is going to have the same rotation number, so that the ergodic measures rotation set it's realize a rotation number by an ergodic measure is more difficult than realizing by a point. And if you have a compact set that has a rotation number, then you always have an ergodic measure supported on this compact invariant set, which means that you're going to have that rotation set Aubry-Matter thing is going to be contained in ergodic rotation set. But the question is, are these things different objects, or are they different or the same? So in the example one, it's let me go back to show the example one. Here you have in example one, you have top boundary has velocity 1, the lower boundary has velocity -1. And then it's easy to see that if you have a point that the average speed of this point is going to be 1, if it's on the top boundary, it's going to be -1 if it's not on the top boundary, because it's going to approximate the lower boundary and start rotating with speed -1. So that the rotation set of points here is just 1 and -1, just the 2 points. While for measures, you can take any convex combination of the two fixed points, one in the top boundary and one in the lower boundary, and you get every number in between. So in this case, the rotation set of the measures is -1, 1, and all the other rotation sets are just the 2 points, -1 and 1. Not the interval, but the 2 points. And in the example 2, then it's much easier to see that for any row in between -1 and 1, you find a circle where you just move, where the dynamic is just a rational rotation of just the rotation of rho. So that in every circle, you find an invariant circle which everybody has rotation number rho. So that the rotation set of Aubrey-Matter in this case, this associated sets are just circles, is the full thing. So that it's clear that the rotation set of measures and the rotation set of points do not need to be the same. But it's not that clear that, well, is the rotation set of points and the rotation set of ergodic measures of Aubrey-Matter or something like that different or not? So question here is, and the questions we are interested here is, and this is an open problem. I mean, we don't know if this is true or not. We don't know if these three things, these three objects, need to be different or not. Okay. So the question here is, okay, so how can you see rotation? What kind of realization of rotation can you see? What kind of phenomena must be present? And if you go now, I'm going to speak a bit about previous results, something which were known in literature. One of the main initial results in this direction is the Poincaré-Birkhoff theorem. It says that if I have a homeo of the annulus which preserves area, and then you have that the top boundary moves with positive speed, and you have the lower boundary moves with negative speed, then you're going to have a fixed point in between. So this is a realization result saying that, oh, if you have one velocity on top, one velocity downstairs, if you have some sort of shear on the top and boundary velocity, and you have the area preservation, then you're going to have a realization of the zero, the in-between speed, by something which is a periodic point. But in this case, by a fixed point, which have this speed. So it's a first type of realization result saying that there was something here that disappeared, but just saying that, okay, that if you have this sort of shear, you have this, you're going to find something else. And then the other very classical case nowadays is the case of twist homeomorphisms. I'm just saying what is a twist homeo. It's just a homeo of the annulus where you take any vertical segment and the image of this segment is some slanted curve. So that it take any points which are in the vertical segments and they push points in different heights, they are going to be moved to different horizontal positions. So that they project locally, they project as the graphs in the first coordinate. And twist maps are things which have natural shear. They appear very naturally in different contexts like billiards and other situations. And for twist homeos, there is a very well-developed theory. It's called the twist diffuse, which preserve area. Then you have Aubrey-Matter theory, which usually use variational techniques, and you can prove that a lot of things are true. Is that that rotation set in this case of the annulus is going to be the Aubrey-Matter set, and the rotation set, the measured rotation set are going to be the same. And the smallest rotation is the one in the bottom. The largest rotation is the one in the top. So that no matter which one in between, you're going to find something that realizes this rotation. If it's a rational point, you're going to find that you actually have a periodic point associated with the rational velocity. If it's not rational, then you're either going to find some invariant curve, an invariant circle, a real circle, or you're going to find a Cantor set with this rotation number. And the dynamics here is semi-conjugated to the rigid rotation. There's a good order properties here, which is a very special thing of twist maps. And something else is that in between these invariant circles, you have some circles which are invariant, which have irrational rotation with different speeds. And what happens in between these two circles is that you have something called a matter region of instability. I'll be more precise defining what is a matter region of stability later, but it's just saying that there are orbits that go, if you have two invariant circles, one on top of the other, then it's an orbit that goes from the bottom circle to the top circle, and there's an orbit that goes from the top circle to the bottom circle. So in between, if you don't have any other invariant circles in no other barriers, then you actually have orbits that goes from one side to from one bottom to from the one end of the annulus to the other end of the annulus, and vice versa. Okay, so then here you always have a lot of stuff. And then if I go now to general analysis homeos, so what can we say about this realization results? And then there's this theorem by Handel first that says that the rotation set of the punctual rotation set is always closed. It's always the closed set. Okay, so then and then if you look at what's the difference between the punctual rotation set and the ergodic rotation set, then the ergodic rotation set, which is containing the punctual rotation set, it's the difference between them. It's a discrete set. You cannot have an accumulation point of points which are in both of them. Okay, it can accumulate in something, but not in them, not in the set itself. So in essence, this says that almost all rotation vector numbers, which you see as rotation numbers of points, are also the rotation number of ergodic measures. But the question here is still, is it always the same or not? This works in general. You don't need to ask for area preservation, but if you go to the area preservation case, then this is a little different. You have a much better result by Franks that says that, well, in this case, if you have a rational point in the rotation set, then there's always a periodic point associated with this rational point, so that the realization question for rational points is always well defined in the area preserving case. There is always a periodic point. And if you combine this with the Handel theorem, this is going to say that the rotation set is going to, the punctual rotation set is going to be the whole interval, because rational points are going to be dense in the rotation set. So this tells you that the rotation set, the punctual rotation set here is going to be the same as the measure rotation set. It follows just that. Well, the measure rotation set is an interval, and then the punctual rotation set just says that every rational there is realized. Handel theorem, Frank's theorem says that, and then Handel theorem says, well, but the set that the punctual rotation set is closed, so that is the whole measure rotation set. It must be equal to the punctual rotation set. But still, you don't know about the ergodic measures or the compact invariant set, rotation sets, the Aubrey-Matter rotation sets. And then you have this theorem by Patrice Lecalves that shows that actually if you go for area preserving C1 diffeos, then the Aubrey-Matter rotation set and the measure rotation set needs to be the same. This was the smallest one and the largest one, and in this situation you're showing that they actually need to be equal. Okay, it is almost solved the question, except for the fact that most of us are guys from C0 dynamics, and we don't like C1 hypothesis. So what can we do more than that? And then what we can do more than that is the main theorem here.
Fabio, I have a question for you. You can show the previous slide. Sorry. In the Handel theorem, you have the numbers which are in the rotation, the punctual rotation, and not realized by ergodic measure. What is the meaning of that? Or there is some explanation for that rotation number?
It's just you can have a point which have a rotation number, but you have no ergodic measure associated with this point. This point does not live in the support of, it's not a typical point of an ergodic measure. And there are examples in the torus where you can always find some points which have some rotation numbers, but no ergodic measures which have the same rotation number with the same properties. Think of this. Just think that you have some sort of in the torus you have some sort of horseshoe that connects one point that moves one up and one point that just stopped. So that, but they don't, in the leaf, they do not connect to the same thing. You have like the unstable manifold of this one crosses the stable manifold of this one, but the stable manifold of this one crosses some translate of the lower one in the leaf. So that when you do symbolic dynamics, you have guys that have some well-precise speed because they spend a lot of time close to one of these 2 points, and these 2 points don't move on the horizontal, but every time you have to make a transition between one point and the other, you move a little bit to the right. And ergodic measures do not have that, because you need to have average, no average movement to the right. So you can find examples when you have a point that realize something, but there is no ergodic measure which associated to it with the same rotation.
Okay, thank you, Fabio.
Okay. And okay, so that's a theorem that is that in fact that this for area preserving, these different concepts that we discussed are all the same. So that means that if you have the weakest thing, which is the measure rotation set, and the strongest thing, which is the Aubrey matrix set, they are the same. If you have any rotation, this is going to be seen by some compact invariant set, which has every point in this rotation. I'm not sure how much time I'll have, so I'll give some basic ideas and try not to extend too much. But the idea here is to define something which is called regions of instability. So the ideas involved, the ingredients involved in the proof are the following. You have to understand what it's a region of instability. You say that an annulus is a region of instability if points that we call the Birkhoff region of instability, if points that are sufficiently low will go sufficiently high, and there are points that are sufficiently high and will have images which are sufficiently low. Meaning that you cannot separate, you cannot have invariant things in between the annulus. You have stuff that goes from very low to very high. You have stuff that goes from very high to very low. And you have a Matter region of instability. It's something stronger than the Birkhoff region of instability, meaning that you have a point that starts downstairs, that the alpha limit is the lower boundary and the omega limit is the top boundary. And you also have a point that the alpha limit is the top boundary and the lower limit is the lower boundary. So the omega limit is the lower boundary. So you move from one side to the other, you have points that actually realize that. These two concepts are not the same. And these two concepts are not the same. There are examples of area preserving, irrational rotations, some not irrational rotations, but pseudo rotations, where everybody has the same rotation number that are transitive, but they are also, they have iterates which are always close to the identity, so that you cannot have orbits that start on the lower boundary and end on the top boundary. But there is a result with Salvador Zanata and myself that shows that at least if your rotation set has is not a single point, then if you have a Birkhoff region of instability, you're always going to have a Matter region of instability. But I'll just treat everything as a Matter region of instability here because it's the strongest one, but it's the one we need for the things we're going to do. And okay, here. And then I need to show a little thing which is called the rotational horseshoe. It's just a horseshoe in the annulus, but the idea is that the horseshoe is like this. When you look on the universal covering, you have this. The Q is usually a square, which gives rise to a horseshoe. But then when you look at it, the image of Q, it intersects in the top in the lift intersects two different copies of Q. One which is in the same fundamental domain, and one which is translated to one fundamental domain to the right. And then if you take the maximum invariant set lambda here, and you code this by some, say R0 is this region. If you end up in this region, R1 is if you end up in this region, then you have a horseshoe here, and if you code the orbits by that, you say, oh, if I see a 0, I stayed at the same place. And if I see a 1, I moved 1 to the right. So then you can calculate the average speeds which points are moving just by looking at the coding of these points by this horseshoe. So you see the coding and you say, okay, I have this coding WI, and okay, if I see a 0, I move 1, I stay. If I see 1, I move 1 to the right. And then my average speed is just the sum of the entries divided by the number of entries. And if this limit exists, then you can say that you have an average speed. And if you use that, you can show that in this situation, for this kind of rotational horseshoe, you can always find for any row, you can find, for instance, the Sturmian sequences of zeros and ones, which have an average row. And this gives you a minimal set in the ship, which has rotation speed rho. And this, when you take the lift of this minimal set, you're going to find an invariant set, which has, everybody has rotation number rho. So this is a good way of constructing invariant sets with a given rotation number. If you have a rotational horseshoe, you always realize anything in between this, the values of the speeds of this horseshoe by compact minimal sets. It's just a symbolic playing with that. You can just use the symbolic coding and the dynamics of the symbolic coding and get what you need here. So this is then what we use here is that there is a previous work that we did with Patrice Calves that shows that if you had a Birkhoff region of instability, if you have an annulus which have these properties of being a region of instability, that you have points going from down to up and up to down, and you have two periodic points with different rotation numbers, then you find what is a topological horseshoe, in this topological rotational horseshoe, in the sense that I described before, like this square that rotates, and for some power of this is a square that intersects two different copies on the lift. And you can see that in this situation, you're going to see that the Aubry-Mater set is going to contain the whole interval between P1 and P2. You find rotation, you find invariant sets for any point there. So, and one of the main ingredients of the proof of the result here, it's this theorem with Jonathan, is first to show that if you have a matter region of instability, then the rotation set is always the same. The Aubry-Mater and the measure is always the same. And just a brief comments on the proof. What's the idea? The first thing is, okay, Frank's result shows that every rational point is realized. So I always have periodic points. And then the result with Patrice shows that any point in the interior of the rotation set is in between two periodic points, two rational points, which means that I have two periodic points associated to them, and I can do a rotational horseshoe and find through the rotational horseshoe that I actually have an invariant set with this irrational speed, which is Aubry-Mater set for that irrational speed. So that takes care of all points in the interior, but you still need to check what happens with the extremal points. Well, one thing is that the extremal points are always realized by ergodic measures. Because as before, remember that the rotation set of measures is just a linear projection. So the extremal points are also the image of the extremal points of the set of the invariant measures. And the set of invariant measures, the extremal points of the set of invariant measures are the ergodic measures. So that the two ends of the intervals are always have associated to them ergodic measures, which realize these 2 points. So then you already know that in this case, the ergodic measure set is going to be everybody, because you knew the interior points and now you have the extremal points. And to go from that to the final thing is that if you have an extremal rotation point, then there are two possibilities. First one is, if it's the rotation number of a point in the boundary, then you just take the boundary as your Aubry-Mater set. And this is easy. But if it's not, then you have to work, and a lot of the work is here, is that you have to use this forcing technique. It's something that I developed with Patrice. I won't have time to discuss this, but the idea is that you use this forcing technique to show that in reality, if this ergodic measure is not supported on the boundaries, then you have some sort of rigidity of displacement. And this rigidity of displacement shows that the support of the ergodic measure is going to be the Aubry-Mater set for the extremal points. So this will take care of the situation when you have a region of instability. And well, but the problem is, if you look at the annulus in general, you don't have only, it's not always that you have a region of instability. And okay, what happens is that sometimes you have some invariant regions and something which lives in between these regions of instability. I'm afraid of putting a blackboard back again. I'm going to draw something here, but if the sound is still working, I think it's better just to say stuff. you have something which separates the annulus in two different components, something called, these are essential continua. So that when you look at the dynamics here, the idea is these are sort of, when you think of the invariant islands up there in the beginning, you had like these curves which separated, and in between curves you had diffusive regions. Here, since these are homeomorphisms, and even for detail, this separating stuff does not need to be invariant curves. This can be just annular continua, just strange compact connected sets that rotate around the annulus, and they can be really nasty. They can be, for instance, a pseudo circle separating the dynamics. And then we already know what happens in between two separating barriers, these two separating sets, because you have regions of instability, and the dynamics there, at least from this point of realization rotation measures, is well understood. But then you still need to understand what happens in these separating sets. What kind of rotation can you see there? Perhaps you have a lot of rotation that happens in these separating sets. So, as I was saying, essential annular continua, they appear as boundaries of regions of instability. And we are especially interested in things that whose interior do not separate the annulus. I don't want a fake essential continua. You could have some sub-annulus as an essential annular continua. I want things that, if you take away that, in some sense, if you just look at the interior, you can connect from down to up. Let me just show one example. This is a Walker example. This is just one example to show. This set, you can see that here, if you think of the plan, take 1 point away and think this is take 1 point away here, where I have here, and you have an annulus. This is a topological annulus. And this set here separates this point. So it separates the plane in two components. So it's sort of it separates an annulus in two different regions. And the dynamics here can have more than one rotation set, even though that my set has no empty interior. It's just a lot of hairs. The idea here is that, okay, the points here rotate with irrational speed, but then in the hairs, everybody moves down. And you can do this in a way that all the points in this limit circle here have rotation number 0. So you have different rotation speeds that can appear for these boundary regions. But then there is a very good work by Andres Koropecki, Patrice Lecoves, and Meisan Nassiri that shows that, at least for the case where you have area preserving, and in the case of area preserving, whenever you have this essential continua, whose interior is not fake, then they can only have one single rotation number. And this rotation number, it's what it's called the prime, it's also the prime end rotation number, but I don't want to get into that. This is just for the specialist who knows what that means. That means that that is the rotation number from the annulus that remains from below and the annulus that remains from above. Okay, so just to give a very quick idea of what is the main, how you complete everything. So the naive idea of how you would get the Aubrey-Matter set is exactly the same as the measure rotation set. You take any number in the rotation set, in the measure rotation set, you want to show that you have a compact invariant set associated to it. You approximate this. If it's just a single point, then it's easy. Every point is going to have the same rotation number, so the Aubrey-Matter is the whole annulus. If not, then the rotation set is an interval, and then you have a sequence of rationals in this interval that accumulates on row 0. And by Frank's result, you can find periodic points Zn, which have rotation rho n, and this rotation rho n converges to rho 0. And then you set the point Z0, which is the limit of the point Zn. And then you start to say, okay, maybe rho Z0 has the rotation number rho 0. Well, it's not that easy. Why it's not that easy? Because rotation numbers are not continuous. So it's not because you have a sequence of points which have rotation rho n and converge to rho 0 that the limit is going to have rotation rho 0. But if this Z0 is in the interior of a region of instability, then you can say, okay, we are done. We already dealt with regions of instability in the previous result. If not, then this set must lie in this invariant essential continua. It's either in a region of instability or is in a boundary of a region of instability. And then you expect the rotation set of the boundary to be rho 0. But again, the problem is that the rotation number is not continuous, so that this invariant region which separates the plane does not need to have the same rotation. So here's where you have to work a little bit more. This will only work if your rotation set was stable. Meaning that if you have any set on the annulus which is stable, meaning that if you start close to it, you don't go far away, and this set has a single rotation number, then points nearby, if they have rotation number, it's going to be close because they are moving with the same speed on the lift. The difference of speed is bounded. And since you're stable, your points that start there don't go far away. So if you want to do something like that, you need to construct something like a stable invariant set that separates the annulus. And well, here's just the technical thing of how you do that. And let me check. Okay. I sort of needed a blackboard for that. If the sound stopped being okay, let me know. And is that you are here in the annulus, okay? And you have your point Z0 here. And you're saying, okay, I have a sequence of points Zn which accumulates in Z0. So what I'm going to do is that I'm going to take a small epsilon ball around Z0, and I start iterating this ball. And I take, oh, the image of this, and the second image, and the third image, and so on. And the fact of the matter is that, okay, if I look at this again, since I have periodic points inside this ball,
at some point, it's silent there now.
Okay. And since you have periodic points, at some point, this has to come back again, and then this ball has to come back again, and at some point, you take this set, which is the U epsilon prime I said there, it's going to be an invariant set. And so the all connected components of this invariant set are periodic. And this can be either a disk, or it can be some region which is an annular region. Okay, so it's either you have some periodic disk here, which is periodic and contains the U epsilon, or it can be something like this. It's a subannulus in some sense. And I claim that this cannot be a periodic disk. Why? Because if you have an invariant periodic disk, well, if you have a periodic disk, topological disk, then every point in this disk needs to have the same rotation number, because this disk is sent to the same disk, so some translate on the lift. But by point Z0 is accumulated by periodic points with different rotation numbers. So you cannot happen that this U epsilon is a topological disk. It needs to be an essential region because you have points in this invariant thing which have different rotation speed. And this essential region, it's an annular region. You can complete it to an annular region. The smallest essential annulus containing this U epsilon. And so here is your U epsilon, and your Z0 lies in the interior here. And then what you do is that, okay, these are invariant regions, and you take this should not be the union, should be the intersection, sorry. You just take the intersection of all these epsilon regions, invariant regions. So you have some U epsilon, then you have some U epsilon prime, and you look what happens. If at the end, what you left is some sort of C, which is some nasty thing here, then this thing is actually a stable continuum, a stable invariant continuum in the sense that we want, because you're taking intersections of smaller and smaller and smaller stuff. And in this case, the previous reasoning work. So if it's stable, the previous reasoning, the one which was sort of naive, actually works in this case. And if it's not, that means that no matter how small the epsilon you take, you have points that start at Z0 and go to the boundary of this region C. So the other case is that when I take the intersections of all this C epsilon, then the intersections will end at something which is my set C, and this set C, which has my Z0 here, now it needs, since I'm starting with points which are arbitrarily close to Z0 and they go here, because that's the idea. This set is just a set of points that passes through arbitrarily close to Z0. Then this region here, it's going to be a region of instability. And that's how it usually works. Okay, so that's how the proof will end. And I mean, I'll need to give a lot more detail, but I think it's confusing enough in this way, just giving the main ingredients. So, okay, and I would just like to thank everybody, and sorry for the technical problems and the confusion in the presentation.
Okay, thank you very much, Fabio. Is there any question?
Fabio, I have sorry.
Yeah, go. Lorenzo. Yes.
I have a question, probably is a silly question. You just, at some moment you define this matter instability and more general stability. I don't know if it's what is the problem if you consider the more restrictive, the less restrictive hypothesis of instability? It's possible to explain this or this?
Okay, so yes. So it was part of the things that I did not draw and talk about. But part of the thing is, let me try draw these. So the two different ideas here is that, okay, I have this cylinder. So the Birkhoff instability is just that if I take some neighborhood U here and some neighborhood V here, I'm going to find some point that goes from here and ends here, and I have some point that goes from up here, then goes down here. So you have, this is doesn't matter which U and V you take, you have points that are arbitrarily low and go arbitrarily high, and you have points that are arbitrarily high and go arbitrarily low. Okay? And the matter definition is a little different, is that you have some point that starts here and dies here on the top boundary, and you have a different point that starts on the top boundary and go down there. This one is stronger than this one, as a clearly. The thing is, it's part of one of the main difficulties here is just, these are technical things, is that realization result that I said here with Conejeros, when I said of region of instability, is that we can only prove that the realization result here, in the way this, particularly this last item here, the techniques here only work in the stronger matter regions of instability, not in the Birkhoff region of instability. And then the technique needs that you have an actual orbit that goes and converges, because the thing is, using the idea with the forcing thing with Patrice, is that you can cut and glue different orbits together. But this only works when you have a very good orbit, and you need the orbits that go from below to the top. So that, but when you do all the work later, what you find is that you have something which are Birkhoff regions of instability, and you have to bridge this gap between the realization result that I set here, which is something I swept under the table in speeding up the last minutes, but between this thing, which is the realization result, which is only work for this weaker thing, and the things that you actually get there, which are on the sort of the scent of the Birkhoff kind, which is the weaker instability regions. But then there is this theorem with Salvador, and actually some intermediate result with Jonathan itself, that says that at least for our particular case, this works. You can even though you have the different definitions and you have a result here for the more restrictive one, you can always find a more restrictive one inside the less restrictive one. It's not that Birkhoff regions of instability are matter regions of instability, but they are close enough from the point of view of rotation. Meaning that if you have a rotation set for one, you find a Birkhoff region with the same rotation set, and you can work just on that. You can find a sufficiently good simile to work with. I'm not sure if it explained a little bit.
I think that is it's okay. Thank you, Fabio.
Okay, Fabio, sorry. What about the hypothesis of area preserving hypothesis? You use it for the existence of periodic orbits and also for the study of the rotation number of essential continua. Is there any other place where you need it?
I don't think so, no. I only use it.
You don't think so?
Yeah. So you're asking if I could use it as just for non-wandering.
Exactly. Yeah.
Okay, so let's go. I use it for the realization result. I use it for the the essential continua would be the most difficult place, I guess, to check everything that it works well. But I think this could be done there. And I think I used it also. No, I think that's it. We might go to non-wandering here, but I'm not sure. I've been nervous and confused enough in this talk, and I'm not good. I don't like having technical problems in between. It sort of threw me off my game. Sorry, guys.
No, it's okay. It's okay. Is there any other question?
Yeah.
I have also a question. Fabio, when you were talking about the topological horseshoe, you talked about minimal sets realizing the rotation number. Is this? I didn't understand.
Yes. So, well, I'm saying that if I just look at the symbolic thing, if I just look at the symbolic coding here, let's say that okay, I'll code things.
Sure. No.
This is on the lift, but if you think of this, you can think of this in the annulus, right? You can go here.
No, this I understand. The construction of the topological horseshoe, I can.
Yes.
Just
Okay.
How do you find the minimal set one number?
Okay, just take the Sturmian sequences just take some, say, whole row here, and then you just rotate. Okay. So again, how do I do that? You just take sequences when you just take zeros and ones, and you just add a 0 and a 1 whenever you it's going to escape me, but just think of, say for instance, you take a Fibonacci sequence of zeros and ones, so that you just take 0 and 1. If you need to add 1, so that the average, if the average is above, you add 1. If the average is below, you add a 0.
Okay.
Okay.
So
you say, okay, I start 0, then I need to put a 1, then I do 0, 0, 1, and you just take the this sequence, and then you take the closure of the orbit of this sequence.
Okay. Okay. Thank you.
Then this is going to be a minimal. This is going to be a minimal set in this case, and the rotation number of every point in this minimal set is going to be the row that you want.
Okay. Thank you.
So that's the easiest way. Okay.
Okay. Thank you.
Okay, any other question?
So if I understood correctly, the main obstruction to get the version of this result with without the area preserving condition is having a result for boundaries, like for annular continua, which are boundaries, right?
Yeah, I think so. I think it's and
because I mean, for the C1 case, the Patrici's result is includes the non-area preserving case, right?
Yeah,
like so basically you need to know that annular continua, which are boundaries, have a realization. Okay.
Yeah, I think that's the main difficulty. Yes. I need to recheck everything, but I think that's the only thing, the most difficult thing here.
All right.
Okay, any other question? Comment? Okay. Thank you very much, Fabio. Very nice talk. I don't know any